Okay, so now that we have seen the first order condition, let's see what it implies for the second order. So I'm gonna work again on that expansion, all right? Let me write what's remaining here. Okay, so we have, all right, so we have x0, y0, an extreme value. Well, f of the value is extreme value, and x0, y0 are actually the arguments where the extreme value happened. So what do we have? We have expansion around that is going to be given, okay, by x0, y0. Okay, let me even go a bit faster and just say, let me put the f of x0, y0 on the other side. So the difference between these is going to be equal to, we already said that the gradient of f x0, y0 is equal to 0. So, all right, let's keep that in mind. So what's remaining is actually going to be the second order term. We have d2f dx2 times h squared plus d2f. So all the derivatives are taken at the point x0, y0. So I've got 1 over 2 here. Here I've got dx dy times h times k plus 1 over 2 d2f dy square times k square, and I should add a small o of the norm square of hk. That's right, norm square. Right. So let's be more specific. It works exactly the same in any case. Let's assume that it's, what should we get? A maximum, right? For instance, what does it mean? It means that this value should be bigger than any value around it. So what does that mean? It means that this thing, if f of x0, y0 is bigger than anything that surrounds it, that should be negative, right? And similarly, if we have a minimum, it means that the f of x0, y0 should be smaller than any value around it, so it should be positive, right? So that means that in a case of, as we've got an equality, let's keep in mind that this is very, very small. The small o is very, very small. That means that if I keep my color blue, light blue, if we have a minimum, that should be greater than 0, and if we have a maximum, that should be smaller than 0. Okay, that makes sense. So in the end, what do we have to do? We have to study the sign of the second order term. Okay, so what are we going to do in that case? Let's see. Okay, that's some kind of trick. So we have to study this thing. 1 over 2 d2f dx squared 0 times h squared plus d2f dx dy x0, y0 times h times k plus 1/2 d2f dy square 0, y0 times k square. So we want to study the sign of this thing. What are we going to do? We're going to divide everything by k square, assuming k is different from 0. K square, k square, k square, sorry, square. Which means that I've now got here, this is h over k to the square. This here becomes h over k, and this here becomes, well, 1, right? So what do we have? We have something like, oh, sorry about this. We have something like a coefficient times something square plus another coefficient times that thing plus a constant value, right? And what is that? That looks like a polynomial of order 2 of the variable h over k. Okay, so that's uh, ax squared plus bx plus c. You see, we have really the sign of this polynomial to study. On this, you know very well how to proceed to study the sign of this polynomial. It's going to depend on the roots. Okay, so what's happening? Let's make the delta. All right, the delta of this polynomial is b squared minus 4ac. Right, so that's going to be d2f dx dy square minus 4 times, well, we've got 1 over 2 times 1 over 2, the coefficients, times the product d2f dx square d2f dy square. Okay, so what's happening then? Well, you have three cases: delta greater than 0, delta smaller than 0, delta equal to 0. Okay, so let's study what's happening in those three cases. The easiest case for what we want to study is going to be the case where delta is smaller than 0. Why is that? Because then our polynomial has no roots. A polynomial of order 2 with no roots, so a polynomial of order 2 is going to be either an upper parabola or a downward parabola, and a polynomial that has roots is a polynomial that meets the x-axis, right? That's one root, that's the second root. If it has no roots, like, well, the downward polynomial that I've drawn here, well, it just means that it's going to have constant sign, or it could have no roots and being an upward-looking parabola. So constant sign does not depend on the values of h and k, right? Whatever the value of h and k, we have that this polynomial is either going to be always positive or always negative. So it has the sign of what is going to be the d2f over dx squared, x0, y0. Okay, it's going to be an upward looking parabola if that term here is positive, or a downward looking parabola if that term is negative. So remember what did it mean? If it's positive, we have a minimum. Okay, we are in that case. We have a minimum, and if it's negative, all right, corresponding to that term being negative, then we have a maximum. Okay, so we find again something similar to the second order conditions in one dimension, right? So which, by the way, I hadn't really stated, but if we, where was that? That was here. You can find again the sign of the second derivative on those drawings here, right? Just by thinking, well, in the case of a minimum, this one, for instance, we have the first derivative is negative, 0, then increasing, it means that itself is increasing. So the second derivative is positive in that case. Whereas here, in the case of a maximum here, we've got first derivative that is positive, 0 negative, so it's decreasing, so the derivative of the derivative, so epsilon is negative in that case, all right? And when f second is equal to 0, we can't conclude. Maybe we are in a case where we have x to the 3 like this, where x second is equal to 0, or maybe we have x to the 4. In the case, we would have a minimum, right? So similarly, we have something like this for the conclusion of that. If the delta is equal to 0, well, actually, it's going to be something like that, where we have roots. So sometimes it's positive, sometimes it's negative. That's exactly the case of saddle point. Oh, sorry, not that case. Sorry. Where we have roots, this is the one. We have a saddle point because sometimes it's going to be positive, or sometimes it's going to be negative, depending on the relative values of h and k. We have a subtle point in that case. And when delta is equal to 0, we can't conclude. Okay, so here you are. You've got the order to sufficient conditions of extreme values, right? It's when we have something like that. So it's all written in the lecture notes, right? You even have everything that we need to to study. All this is reminded in that case, all right, in those conditions. That's Morse theorem, right? And when we've got more than two variables, it will be something very similar. We will still have to study the sign of the order two terms, like the one with the Hessian matrix, HF times the increase which we had denoted k is collaborated with k. So we have to study the sign of this thing, right? So that's it for optimization. So I think it's not you have already studied that you last year. So but I think it was nice to talk about it because we had worked quite a bit on the second order Taylor expansion, which is the basis of it all. Okay, thank you.